In this section, I'm going to discuss the application of the Laplace transform to the design and analysis of feedback control systems. In the world in which we live, control systems are used pervasively. A control system is simply a system that manages the behavior of one or more other systems with some specific goal. Typically, the goal is to force one or more physical quantities to assume particular desired values. Such quantities might include things such as positions, velocities, and accelerations, orientations, forces and torques, temperatures and pressures, and fluid flow rates. The desired values of the quantities being controlled are collectively viewed as the input of the control system, while the actual values of the quantities being controlled are collectively viewed as the output of the control system. An example of a simple control system would be a thermostat system, which controls the temperature in a room. In this case, the input of the system is the desired temperature for the room specified by the thermostat setting, and the output of the system is the actual temperature of the room. One fundamental property of a control system is whether it requires knowledge of the actual values of the quantities being controlled. In the case that this knowledge is not required, the control system is called an open loop or non-feedback system. In the case that this knowledge is required, the control system is called a closed loop or feedback system. Because closed loop systems have more information available to guide them, such systems can be much more effective for control purposes than open loop systems. Consider, for example, the application of a thermostat system. Clearly, it's highly beneficial for the thermostat system to have knowledge of the actual temperature of the room, as would be the case with a closed loop system. By knowing the actual temperature of the room, it's possible for the thermostat system to decide whether it should activate a heater if the room is colder than desired, or an air conditioner if the room is warmer than desired. Furthermore, the thermostat system can also better decide how much heating or cooling is needed based on how much the actual and desired temperatures for the room differ. If the thermostat system had to operate without knowledge of the actual temperature of the room, as in the case of an open loop system, it would be much more difficult for the system to work in an effective manner. At the top of this slide is a block diagram showing the general structure of a feedback control system. In this diagram, the input of the system, sometimes called the reference or set point, corresponds to the desired value of the quantity being controlled. The output of the system corresponds to the actual value of the quantity being controlled. The plant is the system whose behavior is being managed by the control system. The sensor is a device used to measure the actual value of the quantity being controlled, so that this value can be used by the control system in order to adapt its behavior. The adder in the block diagram computes the difference between the actual value of the quantity being controlled as measured by the sensor and the desired value of the quantity being controlled. Thus, the adder output corresponds to an error signal, that is a measure of how much the actual value measured by the sensor deviates from the desired value. The controller, sometimes called a compensator, uses this error signal to decide how to adjust the inputs of the plant in order to force the actual value closer to the desired value. To make some of the ideas introduced here more concrete, let's consider a simple example. In particular, let's consider a thermostat system. A thermostat system is an example of a control system where the quantity being controlled is the temperature of a room. So the output of the system is the actual temperature of the room, and the input of the system is the desired temperature of the room, which is specified by the thermostat temperature setting. The goal of the control system in this case is to force the actual temperature of the room to be as close as possible to the desired temperature. Another example of a control system would be a robot arm. In the control system for a robot arm, the quantities being controlled are the position, velocity, acceleration, and orientation of the end effector of the robot arm in three-dimensional space, where the term end effector simply refers to the device attached to the end of the robot arm, such as a gripper, force torque sensor, or welding torch. Another example of a control system would be the flight control system of some aircraft. In a flight control system, the quantities being controlled are the position, velocity, acceleration, and orientation of the aircraft in three-dimensional space. The input of the system is the desired values for these quantities, while the output of the system is the actual value for these quantities. The desired values are effectively specified through the controls used by the pilot of the aircraft. In order for a system to be of practical use, whether it be a control system or some other type of system, the system typically must be designed to satisfy a number of performance and safety criteria. For obvious reasons, safety criteria are extremely important. In many applications, a critical criterion for safety is bibostability. If a system is not bibostable, this means that a finite input to the system can result in an unbounded, in other words infinite, output. Since the output of a system typically corresponds to some physical quantity, an unbounded output would correspond to some physical quantity becoming infinite. Needless to say, a physical quantity such as temperature or force becoming infinite is fundamentally incompatible with human life, as well as most other forms of life. Therefore, a system that is not bibostable is quite likely to injure or kill humans as well as other life forms. Of course, in practice it's not good enough that a system simply be safe, for example, not kill anyone. Such a system will also need to satisfy a number of performance criteria. For example, in the case of a thermostat system, the system might be required to make guarantees about how quickly it can respond to changes in the desired or actual temperature. As it turns out, the Laplace transform is a very useful tool for designing and analyzing systems, including systems with feedback. By using the Laplace transform, we can ensure that a system meets the performance and safety criteria required by a particular application. As we saw earlier, in the case of an LTI system, the bibostability criterion is extremely easy to test in the Laplace domain by considering the region of convergence of the system function of the system. Therefore, the bibostability of LTI systems is often analyzed in the Laplace domain. At this point, I'd like to consider two examples illustrating the use of the Laplace transform to design or analyze feedback systems. First, I'd like to consider example 7.40. In this example, we're given a causal LTI plant with the system function p given by this particular formula here. Then we're asked to do the following. First, we're asked to show that this plant is not bibostable. Then we're asked to stabilize this unstable system using two different methods. The first method is using pole zero cancellation, and the second method is using feedback. Lastly, we're asked to identify any practical issues with either of these methods. So first, we proceed to show that the plant is not bibostable. To begin, we observe that the system function of this plant has a single pole at 1, in other words, this pole here in the complex plane. Furthermore, because the system is causal, the region of convergence of this system function p must be this right half plane that's shaded here to the right of the pole. Because this region of convergence doesn't include the imaginary axis, the system is not bibostable. In the next part of this example, we're asked to show that the unstable plant can be stabilized by connecting it in series with the causal LTI compensator with the system function w, where w is given by this particular formula here. So now let's proceed to show that the system depicted in the block diagram is bibostable. First, we can observe that since the compensator and plant are connected in series with one another, as is shown in the block diagram here, the system function h of the overall system is given by the product of w and p. In other words, we have this equation here. Next, we can substitute in for w and p the formulas that were given for these functions, in other words, these functions here. This gives us this next expression. We can then cancel the common factors between the numerator and denominator, and when we do this, we obtain this expression here. In other words, the system function h has a single pole at -1, which corresponds to this pole here shown in the diagram. And the region of convergence of the system function must converge to the right of this pole because the system is causal, therefore it must have a right half-plane region of convergence. And then lastly, because this region of convergence includes the imaginary axis, the system is stable. Lastly, it's important to observe that this approach to stabilizing the unstable plant is based on pole zero cancellation. Recall from earlier that the reason that the plant fails to be bibostable is due to its system function having a pole at 1. This undesirable pole is associated with this s-1 factor here in the denominator. In the approach to stabilization that we're using here, we're eliminating this pole by canceling it with a 0 at the same location. This 0 is associated with this s-1 factor in the numerator here. So fundamentally, this stabilization technique relies on pole zero cancellation. In the next part of this example, we're asked to show that the unstable plant can be stabilized by connecting it with a causal LTI compensator and sensor in the manner shown in the block diagram here. In this block diagram, the sensor has the system function q, where q is given by this particular formula here. And the compensator has the system function c, where c is given by this particular formula here, and beta is a real constant. As we'll see shortly, the stabilization method being used here does not rely on pole zero cancellation. Rather, it relies on the fact that the particular system interconnection scheme shown in the block diagram utilizes feedback. So now let's proceed to show that the system depicted in the block diagram is bibostable with an appropriate choice of the constant beta. From a careful analysis of the system, we can show that the system function h of the overall system is given by this particular formula here. We'll derive this formula shortly, but for the time being we'll simply use this result. If we substitute the functions cp and q that were given into this formula, in other words substitute these functions here, this gives us this next expression here for h. In other words, h has a single pole at 1 minus 10 beta. This corresponds to the pole shown in the diagram here. Furthermore, because the system is causal, we know the region of convergence of the system function must be a right half plane. Therefore, it must be to the right of this pole, in other words, this blue shaded region here. Observe now that if this pole is strictly to the left of the imaginary axis, then this shaded region will include the imaginary axis and the system will be bibostable. So therefore we have the condition that if 1 minus 10 beta is less than 0, in other words this condition here is satisfied, the system will be bibostable. Furthermore, we can rearrange this inequality and solve for beta to obtain beta is greater than 1/10. Therefore, we conclude that the system shown in the block diagram will be bibostable provided beta is greater than 1/10. In order to complete this part of the example, it still remains for us to show how the formula for h was derived. This is what we'll do next. On this slide, we're going to derive the formula for the system function h of the overall system shown in the block diagram in terms of the functions c, p, and q. To begin, we label each point in the block diagram with the formula for the signal that appears at that point. This is helpful to do as it will allow us to more easily write some equations characterizing the system shown in the block diagram. First, let's label this particular signal here. So this signal is the output of an LTI system with system function c, and the input to this system is r. So the output will be the product of r and c, which gives us r times c here. Let's consider now this signal here. This signal here is the output of an LTI system whose system function is p. The input to this system is r times c. Therefore the output will be the product of r times c and the system function p, in other words r times c times p. Lastly, let's consider this signal here. This signal here is the output of an LTI system whose system function is q. The input to this system is y, therefore the output will be y times q, which is this particular formula here. Next, we proceed to write an equation for the output of the system and the output of each adder. So let's consider each adder. Well, there's only one, which is this one here. So if we write an equation for this adder, what we'll have is the output of the adder, which is R, is equal to this input x minus this bottom input, which is y times q. So this gives us this particular equation here. Next, we write an equation for the output of the system. Here we have the output of the system, which is labeled by two formulas. It's labeled by y, but it's also labeled by r times c times p. So these two quantities must be equal. Therefore, we have this second equation here. Now what we'll do next is we'll use this second equation as our basis for going forward, and we'll just copy this equation below here. And what we'll do next is we're going to substitute for r in this equation the formula for r given by equation 1, in other words, this equation here. This gives us this next line. Then we can multiply this c times p into the quantity in square brackets, which gives us this next line. Then we can move all the terms that involve y over to the left-hand side of the equation and factor to obtain this next line here. And then lastly, we can divide both sides of the equation by x times 1 plus cpq. In other words, this expression in the annotation here. When we do this, this gives us this particular equation here. Then lastly, we observe that because the system is LTI, we have that y is equal to x times h, which means that h is equal to y over x. So we can observe that y over x here is simply equal to h. Therefore, overall, we have that h is given by this particular formula here, which is what we were trying to show. On this slide, we're going to start with the formula for h that we had at the bottom of the previous slide, namely this formula here, and we're going to substitute for the functions cp and q that appear in this formula, the functions that were actually given for cp and q, namely these formulas here. When we do this, we obtain this next line here. We can then multiply the numerator and denominator by s minus 1 to obtain this next line. And lastly, we can rewrite this rational function to explicitly show its pole. In particular, it has a pole at 1 minus 10 beta, which gives us this last line. So now we have an expression for h of s, which is given by this particular formula here. And this is the result that we were trying to show. In the last part of the example, we were asked to identify any practical issues associated with either of the methods used to stabilize the unstable plant. In this regard, we can make the following important observations. The stabilization method based on pole zero cancellation will not work in practice. This is due to the fact that pole zero cancellation cannot be achieved in practice. The theoretical models used to represent real-world systems are only approximations due to many factors, including the following. Firstly, determining the system function of a system involves measurement, which always incurs some error. Secondly, a system cannot be built with such precision that it will have exactly some prescribed system function, so the system function of any system that we manufacture will always differ at least slightly from what it should be. Thirdly, the system function of most systems will vary at least slightly with changes in the physical environment. This causes the system function to differ from what we expect it to be, which incurs error. Lastly, although an LTI model is used to represent a system, the likely reality is that the system is not exactly LTI, which introduces error. Due to error introduced by factors such as these, the effective poles and zeros of functions will only be approximately where they're expected to be. Since pole zero cancellation requires that a pole and zero be placed at exactly the same location, any error, however small, will prevent this cancellation from occurring. In contrast, the stabilization method based on feedback does not suffer from similar problems. With the feedback approach, instead of trying to cancel poles, we simply change the poles of the system function completely. When we do this, we can keep the poles sufficiently far away from undesirable regions that approximation error could not result in any poles moving into any of these regions. For this reason, the use of feedback to stabilize unstable systems can be made to work in practice. Next, I'd like to consider exercise 7.30. In this example, we're given this system script H with input Laplace transform x and output Laplace transform y, as shown in the block diagram. And we're also told that each subsystem in the block diagram is LTI and causal and labeled with its system function. Moreover, we're also told that the quantity A appearing in the block diagram is a real constant. Then we're asked to do two things. In part A of the example, we're asked to find the system function h of the system script h. In part B of the example, we're asked to determine if the system script h is bibostable. So let's proceed to do part A of the example. In this part of the example, we need to find the system function h of the system shown in the block diagram. To begin, we note that a systematic approach for solving a problem like this is given in this annotation here. This systematic approach consists of the following four steps in order. Firstly, we label the system input and system output if they're not already labeled. Secondly, we label each adder output that's not already labeled. Thirdly, we write an equation for the system output and each adder output. And then lastly, we combine these equations to obtain the system function. In what follows, we'll adopt this systematic approach for our solution. Since the system input, system output, and adder outputs in the block diagram are already labeled, the first two steps in our systematic approach are complete. In the third step of our systematic approach, we need to write an equation for the system output and each adder output. In order to do this more easily, we're going to first label each point in the block diagram with the formula for the signal that appears at that point. This is helpful to do as it will allow us to more easily write equations for the system output and adder outputs. First, let's consider this signal here in the block diagram. This signal is the output of an LTI system with system function 1 over s, where the input to this system is given by v. Therefore, the output of this system will be v times 1 over s, which is this formula here. Now let's consider this signal at this point in the block diagram. This is the output of an LTI system with system function 1 over s, and the input to this system is the formula that we just found here. Therefore, the output of this system will be the product of this formula here, in other words, the input to the system, and the system function 1 over s, which gives us this particular formula here. Now let's consider this signal. This signal is the output of an LTI system whose system function is minus 3. The input to this system was what we found previously. It's 1 over s times v of s. Therefore, the output of this system, in other words, this signal here, will be the product of 1 over s times v of s and minus 3, which gives us this formula here. Now let's consider this signal at this point in the block diagram. This signal is the output of an LTI system with system function minus 4, and the input to this LTI system is this given by this formula here that we computed previously. Therefore, the output of this system will be the product of this formula here, which is the input to the system, and the system function minus 4, which gives us this formula here. Now let's consider this signal here. This signal here is the output of an LTI system with system function a. The input to this system is given by this formula which we found previously, 1 over s times v of s. Therefore, the output of this system, in other words, this signal here, is given by 1 over s times v of s, in other words, this formula here, times a, which gives us this formula here. Lastly, let's consider this signal here in the block diagram. This signal is the output of an LTI system with system function 2. The input to this system is given by this particular formula here that we found previously. Therefore, the output of this system will be equal to this function here in the annotation times 2, which gives us this formula here. With all of the signals appearing in the block diagram now labeled with formulas, we can easily write equations for the system output and each of the adder outputs. First, let's consider the leftmost adder in the block diagram, in other words, this adder here. The output of the adder is denoted V, and V is equal to the sum of three inputs, namely this input here, which is equal to x, this input down here, which is equal to minus 4 over s squared times V of s, and this input here, which is equal to minus 3 over s times V of s. So from this adder, we can write this equation below, which is labeled as equation number 2. Next, let's consider the rightmost adder in the block diagram, in other words, this adder here. The output of this adder is labeled as y, and this output is equal to the sum of three inputs. This input here, which is equal to v, this input here, which is equal to a over s times V of s, and this input here, which is equal to 2 over s squared times V of s. So from this adder, we can write this equation here, which is labeled as equation number 1. Since the rightmost adder output is also the output of the system, we've already written an equation for the system output, namely equation 1. So we've completed the third step in our systematic approach to the problem. At this point, I'm going to pause in order to scroll the example upwards so that we can see the remainder of the solution. Now we continue from where we had left off. Recall that we had just finished deriving equations 1 and 2, in other words, these equations here. The last step in our systematic approach is to combine these equations in order to determine the system function. To accomplish this, we proceed as follows. First, in equation 1, we factor V of s out of all the terms on the right-hand side. This gives us this new equation here. Then in equation 2, we move all the terms involving V of s to the right-hand side of the equation and move all other terms to the left-hand side. And then we factor V of s out of the terms on the right-hand side. This gives us this equation here. Now we take this equation here, which is labeled as equation number 3, and we divide it by this equation here, which is labeled as equation 4. Doing this yields this equation here. Then we can simplify the right-hand side of this equation to this expression here, and we can simplify the left-hand side of this equation to simply h of s. The reason we can simplify the left-hand side of the equation in this way is the following. Because the system we're dealing with is LTI, we know that y of s is equal to x of s times h of s. Rearranging this equation and solving for h of s gives us h of s is equal to y of s over x of s. Therefore, we can replace y of s over x of s by h of s. So now we have h of s is given by this particular expression here. At this point, we now need to find the poles of the function h in order to test the system for stability. So using the quadratic formula, we can determine the poles of h to be as given here. What's important to note about these poles is that they have negative real parts. The reason this is important is because the region of convergence of the system function must be a right half plane due to the fact that the system is causal. In particular, it must be a right half plane to the right of these poles. Because the poles have negative real parts, the region to the right of these poles must include the imaginary axis. Therefore, the system must be stable.